Okay, perfect. I think we can start. Good morning, everyone. Thank you for joining us for the final event of the Residue project. After 4 years of fruitful collaboration among all the project partners, the Residue project is coming to its end. And over the next 2 hours, we will present the main results achieved during these years. So if someone from the audience has questions, you can directly write in the chat. We will take some minutes after each presentation to answer. And so now I would like to introduce the first speaker, Dieter Hennecke from the Fraunhofer Institute as the coordinator of the Residue project. He will give you some insights and an overview of the Residue project.
Okay, thank you very much, Melissa. Can you see the screen now? Okay, now it starts. Yeah, thank you very much and welcome to everyone listening to this event or joining this event here. I would like to give some brief introductory words before we start with a real scientific work. The residue, final event residue, you see here, it means risk reduction of chemical residues in soils and crops, impact due to wastewater used for irrigation. Next slide, please. And first, probably a word about PRIMA. PRIMA is a partnership for research and innovation in the Mediterranean area. And in brief, it is funding projects for looking for innovative solutions for water provision and water management in the Mediterranean area, because due to this climate change, it will even get worse in the coming years. The water scarcity in this lands on these areas or countries around the Mediterranean area. Next slide, please. So our idea from the Residue project, or the problem behind the Residue project, is that these countries, when you don't have enough water, you have to use each water or every water that you can get for agriculture. And in many countries, this is wastewater after treatment. And after treatment, it might happen that some anthropogenic chemicals, organic contaminants, are still in the irrigation water, and via this water it will come to the soils, and via the soils to the plants. And the problem is then there's a risk of food contamination by uptake from the crops. Next slide, please. As you could see before, there's in between the irrigation water and the crop, there is a soil. And the soil serves important functions. Soil can also filter chemicals, it can trap it or can degrade chemicals. The retention of chemicals is a very important process in soils. And a very important soil parameter that influences all these processes is the soil organic matter. And it depends on the quantity and quality of the soil organic matter, how the soil can work in this important function. This is very important. Next slide, please. Because our idea was not to set new limits to, let's say, to irrigate to contaminant concentrations in irrigation waters, because it's not easy to simply get these limits. What do you do if the limits are exceeded? You have to use the water anyway. So that is not the point for us, but we want to reduce the risk of the transfer of this organic contaminants once it comes to the agricultural land by improvement of the soil functions. So our approach is to go to the soil, improve the soil functions, and so to avoid contamination of the crops you grow there. And everything should be, of course, sustainable. That means we use a material which is local waste material. We treat it in a way that it improves in the end the soils. And this is for us is not only sustainable, but also cost effective. And this is a way that the local farmers can use it. Next slide, please. These are the project partners in the PRIMA project. I think you will see them all later in the presentation, so I don't want to go into detail with this. But you see Israel, Spain, Germany, Italy, other countries which attend this project. Next slide, please. And this is a project structure. Yeah, it's a bit little. I just want to go with it in brief. The work package 1, where we had to check, okay, which local waste streams are available, what are the substances of interest. Then the work package 2, to produce a substrate. That was one of the most important steps, to produce a substrate from the local waste, from the local materials. And with this substrate, we went to the soils and we checked it, and we were investigating this substrate scientifically in the other work packages 3, 4, 5, and 6 to look if it serves as it should serve, to protect it, or to improve the soil functions. Work package 7, very important from Italbiotec, is a dissemination. So to have not only have scientific results, but also move it to the farmers or transfer it to the farmers that it gets used in the end, to kind of bridge this valley of death, what you have very often from scientific projects. And work package 8 in the end is a data management scientific report. We're actually in the phase of reporting. Next slide, please. Very brief, these were the reference contaminants selected, but it will come probably also later in another slide. It was carbamazepine and lamotrigine, which was also found already before we started the project from in projects in Israel. And this is what we selected, and especially these were now radio labeled, but I think Kerstin will tell this later. Next slide, please. Yeah, okay, next slide. For the time schedule, you see the original time schedule was 3 years. In the end, we had to extend to 4 years. And you see on the right side up, we had some unexpected challenges. Some were scientifically, like the composting with the biochar, which did not work as we thought. I mean, it was the first time someone did that, and we had to learn a bit how to adjust it, and now it works really perfect, very good. And due to this delay, we got a radiolysis of the test substance, which needed to be purified later. Also details, I think, will come later from Kerstin. And all in between with the COVID crisis, and in the end, since last year, then the war in Israel, which affected everything very much, the project. So I think we are pretty happy to have it done now in 4 years with very good results, but the extension of the project for 1 year was necessary. Next slide, please. Yeah, before I come to the project, to the program today, I have some impressions. It's all photos from the partners. I think they will show some more photos. And again, thanks to all the partners here for this great project, to work with you. I hope there will be some coming projects in the future. Yeah, after we finish this one here. Next slide, please. This is a program. That means every partner will present their part of the overall residue project, and I think I give over to Melissa again. Thank you very much.
Thank you very much, Dieter. So if there are no questions, maybe there will be questions or more specific topics that will be given later. So I will give the floor to the second speaker, Dimitri Dabkin from the Freie Universität of Berlin.
Yes, okay.
Thank you.
You see the presentation, yeah?
Yes.
Okay. So I will start on the characterization of this waste materials that I already mentioned. Go on. Okay. So now you see this two different materials actually that we used in the project. These are the pictures from the project partner in Israel. You see the sewage sludge compost, and you see on the left side, and you see the produced biochar that was produced from the waste, partially from this compost, sewage sludge compost itself, and with addition of wooden residues. So just to give you an impression of the materials that we used, when we analyze them, we see actually that we first of all, before we actually got the opportunity to use the biochar produced from sewage sludge compost itself. We also carbonizated the composted sewage sludge by ourselves. And here you just see the comparison of the values with some limit values on the right side of EBC, which is European biochar certificate, and also the comparison with Israeli regulation for sewage sludge use. So you first of all see that the composted sewage sludge is already line in the limits of the Israeli regulation, and you see, for example, that the biochar or carbonizate that we produced from the composted sludge, it just accumulates heavy metals, so they are not gone. Somehow during the carbonization process, they will just accumulate because, of course, the mass is reducing. So from the point of heavy metals, it then doesn't look very good. But okay, if you compare, if you see the next large biochar which we used in the project from Israel, it's already looks better. But it's effectively product that is produced from the mix of carbonizated mix of composted sludge and wooden residues in the percentage of some 50 to 50 volume percent, and this already gets much better results concerning heavy metal content, although there are some still some values that are higher in comparison, for example, to the European biochar certificate. You see it's concerning copper and zinc. But anyway, that they are still very under the values from the Israeli sewage sludge regulation. From the organic point of organic contaminants, you see benzoapirin is really still under the limit values. You see some problem with the large biochar that was produced in Israel concerning this some parameter of 16 PAH. But if you look at our carbonizates that we produced here in Germany, you see it's just some sort of technological problem which can be solved. So it's really not a problem that is with heavy metals that is just there, but this is something that is due to some technological aspects, and it's not a problem. It's something that can be solved with a better processing design. Okay, concerning the nutritions, you see also the nutritions total values are accumulated, and you see it in our produced biochar, and they are also in a way diluted in the sludge biochar that we used that was produced in Israel with partially with wooden residues, but you still see in comparison high nutrition values for this product. One important thing is also this ratio of hydrogen to carbon and also oxygen to carbon. It just shows the stability of biochar that is produced, and you see that effectively all the biochars, so these are, for example, the biochars that we produced at different temperatures from the compost, sludge compost, and with 500 to 550, this is indicated the sludge biochar that we used in the trial from Israel. And they all lie in this field that is indicating a good stability of biochar, and it is an important characteristic because it means this material will stay in soil and will not decay lightly. And so our biochar is comparable with this, for example, these blue points that are from the foliage, done from the foliage. Of course, the best values are the you can get as from wooden material, but anyway, all is in this field of high stability. So what we actually did, we made leaching tests, column percolation tests with these materials, and they were done according to German industrial norm, which is the water is coming upside down from bottom to top, just to make sure that the saturation is done well in the column. You take different liquid solid ratios, and okay, I just go to the results a bit, and first of all to some characteristics of the trial. So we put some 2/3 of the column were filled with soil from Israel, with the sandy soil from southern Israel, and the top, or actually bottom in the trial, but which is a top actually. When we simulated, it was filled, it was 1/3 of the column, and the soil was mixed with 7% of this compost biochar mix that we used as an application, as an agricultural application. And it actually simulates the way, the amount and the way it is applicated in Israel. So that was the point. And we used the water spiked with 1,000 nanogram per liter carbamazepine, also to simulate the standard wastewater application. We collected 3 liquid to solid ratio fractions, 1, 2, and 4. And we also made a trial also with water application only, which is also was not unspiked with carbamazepine, because we have to have some sort of blind value, because to account for carbamazepine that is just in the sludge itself, and is washed out from the material. So it's how it looks like. Actually, the material, we just have only 7% mix in the soil, so you don't see much in this top soil layer, but we actually saw something when it was saturated, it was really different from the soil itself. So this 1/3 with 7% material mix, we already saw that it was much blacker, more black part when this column was saturated. So the results. If we look, if we compare this soil that was applied with unspiked water and with a spiked carbamazepine spiked water, we see that we have the difference in the fractions. And the first fraction almost all comes from the material itself, you see. And in the liquid solid fraction 2 and 4, the most carbamazepine in resulting comes out from the water, spiked water applied. So we don't take the first fraction into account, because almost everything comes from the material itself. And you really see the effect in the fractions 2 and 4. And you see the reduction of the amount of carbamazepine in the resulting eluate. We actually don't see much difference between applications. You see here the legend on the right side with 10, 20, and 30% biochar mixed into the compost, but we see the difference between the control without biochar mixed and biochar applications. And we actually see pretty good the reduction of the amount of carbamazepine in the elute. When we put it as a percentage of carbamazepine that we applicated in total to the columns, we see you can see that the retention of carbamazepine is pretty high with the biochar amendment in comparison to the control. So in the second fraction from 17.5 to some 50%, and in the fraction 4, liquid to soil 4, 1 to even 25, 35%. So the effect is there. Concerning, this was of course our main goal in the project to see this fate of carbamazepine, but we also looked at the washing out of heavy metals, and you see that just in percent of the total content in the soil or in the mix, and you see that only a very small number of amount of heavy metals is washed out and effectively is bioavailable in these materials, in these soil columns. You also see that we also have here some reduction with the biochar amendment, but it's generally on a very low amounts, and it's not really to mention. So we have coming to the summary, we have very low amount of heavy metals in the leachate. It's not bioavailable here, and our main result is showing a decrease of carbamazepine in the elute, which is corresponding to the increased retention in the substrates with biochar amendment. So once more against the control, and we don't see much difference between different biochar amendments with 10 to 30%. So we can conclude that already with 10% biochar we get the main effect, and the result main effect against the unamendment substrate. Okay, thank you. And this was first things concerning the characterization and retention of carbamazepine in the material.
Thank you very much. If there are any question, you can write in the chat, or if you have them later, we can just take some time after all the sessions. So I don't see any questions for now. Okay, so maybe let's go on with the third presentation. So I will leave the floor to Guy Rosner from the Peter Lab and the Hebrew University of Jerusalem. So the floor is yours.
Thank you, Melissa. Can you see the presentation?
Yes.
Okay, Hello, everybody. My name is Guy, and my project is mainly about compost and biochar amendment and their effects on plant uptake of wastewater-derived contaminants. I won't go into a lot of previous, but I will speak about the use of treated wastewater in Israel. Israel is a pioneer in the reuse in treated wastewater. Around 84% of the total production of wastewater is used for irrigation. So it's a great solution for the global water crisis. And the product that we are using in our research is the biochar, the compost, and the treated wastewater. But despite its obvious benefits, there is a lot of persistent compounds identified in the treated wastewater, especially pharmaceuticals, endocrine disrupt contaminants. Of a list of contaminants found in treated wastewater, it is important to remember that their new contaminants are constantly identified. And my research objective is to study the effect of application medium, especially we are going to use compost, biochar, and treated wastewater, and to see how the alfalfa plant is uptaking these contaminants. So how everything was done. We chose alfalfa for our cultivation. Alfalfa is a perennial plant, so we can cut it every time and it will regenerate by itself. Every harvest we cut, the plant material was freeze-dried, grind, and wait before analysis. The growing period was 185 days. Out of it, 122 days was irrigated only with treated wastewater. We had several harvests, six times. After the extraction, all the extraction has been identified and quantified using LCMS machine. So how was the greenhouse experiment was done? First, we choose the near old soil, as Dimitri said earlier. The composition of the soil is with low clay content and low organic matter content in order to reduce the sorption processes to the soil. We fill the pot, 2/3 of the pot with the soil, and we added organic amendment, either 0%, no, and 1.5%. In a 1.5% amendment, we have only biochar, only compost, or the combination between both of them. So we have total 4 treatments that were duplicated for irrigation, either with treated wastewater or with fresh water. Now let's go to see the first result. First result will be the alfalfa plant's growth fresh weight. On the x-axis, we can see the different treatments, and on the y-axis, we have the fresh weight in tons per hectare. The red line is indicated and reported by the Ministry of Agriculture that the first year of harvest of alfalfa plant will be 17 tons per hectare. Our average was 18, besides 2 treatments that were behaved differently, probably maybe because of the biochar salinity or inhibitory of seed germination. And now let's go and see the result for the shoot concentration. In this graph, we can see on the y-axis the concentration in nanogram per gram. The x-axis will be the days since sowing and the harvest number, 2, 3, 4, 5, and 6. Each bar represents different treatment. And we saw that in all of the treatments, we have similar trend. So because we saw similar trend, I combined them all together to receive an accuracy result that based on bigger statistic. And now let's look on combined graph. Okay. First is this, on the x-axis, it's the treatment, y-axis is the concentration. And now let's look only about the treated wastewater irrigation with the treatment. First, let's look about the blue bar. The blue bar represents the treated wastewater irrigation without any organic amendment. As we expected to see, because there was low organic matter content and clay content, the bioavailability for plants uptake should be high. So the highest concentration is found in this treatment. Now let's look on the rest of the treatment. Each treatment has has decreased, the concentration has decreased in all of the other treatment. Now, the main point here is the quality and the quantity and the quality of the organic matter we use. The orange bar is the compost, the green bar is the combination between the biochar and the compost, and the red bar is the biochar amended soil. The major decrease was between the biochar and the treated wastewater. The average decrease was 84%, which is a major found for us. And now let's look about freshwater treatment amended with the compost or the biochar. We saw that the biochar uptake was 0, and the freshwater with the compost has released contaminants to the plants uptake. So now let's go and look deeper into these two treatments. This graph is performing from the second harvest. We see on the y-axis, again, concentration in nanogram per gram, and on the x-axis, we see freshwater with compost and freshwater with biochar. The freshwater with the compost, we see that the compost has released contaminants to the shoots, and the biochar we did not detect it. Probably because the carbamazepine is eliminated because of the pyrolysis process. And now let's look again more deep into how the compost is acting as a source for the contaminants. So this results showing the days in sowing, second harvest, third, fourth, fifth, and sixth. We see that there is a decrease in the concentration in the shoots of the freshwater of the plants in the freshwater with the compost. This is probably due to the degradation of the compost. Because of that, there is a more adsorptive side. Therefore, the bioavailability for plants uptake is decreasing, and the amount of the carbamazepine for uptake is also decreasing. So this result for now is showing us the concentration in the shoots. And now let's talk about the soil. I didn't mention earlier, but at the end of the experiment, before I throw everything, I took soil samples. I took from the top, middle, and the bottom of the pots. And also just to understand how the balance between the concentration in the shoots and in the soil. This graph is performing for carbamazepine in the near all soil profile at the end of the growing season. The x-axis is the concentration in microgram per kilogram soil. We can see the different depths. And now let's look only on the blue bar. Again, the treated wastewater treatment. At this treatment, we expected to see a similar concentration in all of the layers because there was a good transport of the carbamazepine through the soil layer. This results probably because there was no or a low organic matter content in the soil. And we expected to see different results for the other treatment. And now the other treatments, we can see that the highest concentration found in the pot was in the treatment that was amended with biochar. And it fits to our previous result that we saw that the lowest concentration of carbamazepine in the shoots was detected in the soil amended with the biochar. And what is interesting to see is that in the deeper layer, we saw a really a low amount of the contaminant of carbamazepine compared to the top layer. Sorry. And now we can see the same trend for another compound, lamotrigine, which is another anticonvulsant agent. And it's again remind us the importance of organic amendment, and biochar is binding contaminants more than compost or the combination between both of them. So after that, we saw that the concentration in the soil is greater than in the shoots if the pot was amended with organic. And now let's look about a factor that is called bioaccumulation factor, which was calculated by the division of the shoot concentration to the soil concentration. If the number is greater than 1, it's indicated that the concentration in the plant is greater than in the soil. Again, let's look only on the small bar, on the left bar, on the treated wastewater treatment. We see that the factor is around 3, which indicates how much the bioavailability for plants uptake is relatively high compared to the other bars. If we see the compost in here or the combination, we see also a decrease in the factor, but the lowest factor was determined in the treated wastewater treatment amended with the biochar. The factor was around 0.25, which indicates how much the bioavailability is relatively low compared to the other treatments. So this is for now. The conclusion of my research is that biosolids, either compost or biochar, may act as a source for contaminants when combined with fresh water, or they can act as a source or a sink when combined with treated wastewater irrigation. The composted biosolids and the biochar effectively decrease the bioavailability for the contaminants, and the notable reduction in the contaminants highlights the potential of biochar as a highly effective soil amendment for reducing the bioavailability and keeping our health safety. I would like to thank all the partners who were involved in this project and everyone who supported me over the last 2 years. Thank you very much, and a special thanks to PRIMA for funding research on water management in the Mediterranean area. Thank you very much.
Thank you very much, Guy. Just a few seconds to see if there are some questions. Okay. So we can move on. Thank you again. We can move on to the next presentation from Kerstin Dertz from the Fraunhofer Institute.
So you can hear me now?
Yes, now we can hear you.
So again, I'd like to share my screen. So can you see the presentation now?
Yes, perfectly.
Thank you. Yeah, my name is Kerstin Dertz. I would like to present the results of our work package at Fraunhofer IME regarding the planned uptake of the two specific pharmaceuticals, carbamazepine and lamotrigine, from soil amended with compost and biochar. And in addition to the investigations performed at the Hebrew University in Jerusalem, we used radio-labeled compounds to provide additional information regarding the fate of these two pharmaceuticals during the cultivation on areas irrigated with treated wastewater and with soil amendments. So, yes, yeah, the climate is different in Israel and in Germany. So we are using the greenhouse, and we are also selecting experimental conditions which should be as comparable or as similar as possible to those used in Israel. So we cultivated also alfalfa plants. We used stainless steel containers, but they were also filled with the same soil, with the near-earth soil, and we use also the same amendments, so the same compost and the same biochar. We have also performed a drip irrigation during the cultivation of plants, in our case with artificial wastewater, including either radio-labeled lamotrigine or radio-labeled carbamazepine. And here you can see also the tubing of the containers. Here in these canisters there are the artificial wastewater or the fresh water also in, and which is then pumped. Can you wait? I try to get my laser pointer, which is then pumped through the this pump onto the area 3 times a day, so that the plants can grow. And we have then done 6 successive harvests, as also was done in Israel, and we harvested the above ground plant parts, so that we can get plant material ready for investigation of the uptake of the radio label. And we have 2 sets of containers. One set of container is applied with carbamazepine. You can see the molecule or the structure of the molecule here, and you also see which C12 carbons are now 14C carbons, so that it is radiolabeled in the ring, and another set of the containers is applied with lamotrigine, and also here the structure of the lamotrigine molecule. 1 container of each set is amended with the sludge compost only, and then other containers are amended with a compost biochar mixture. 1 contains 10%, 20%, and 30% of biochar. So these are the 4 amendments which we have tested in our test set. And here you have a photo of our greenhouse trial. On the left side, we have the containers of the carbamazepine treatment, and on the right side, the containers were treated with artificial wastewater, including lamotrigine, radiolabeled lamotrigine. And the first container here is the soil amended with a compost only, and then the other containers include the amendment of 10 compost biochar mixture with 10%, 20%, and the last one with 30% biochar. Yes, and then you see we have cut the plants about a height of 10 centimeter above ground. So we have a pooled a sample of all plants on 1 container, and the plant material is then stored frozen immediately. And then the plants are growing, and we have done 6 harvests. In the lab, the frozen plant material is homogenized by milling using dry ice, so that it is still freeze, and in the end it is a homogeneous powder. In the second step, we have determined the total radioactive residues. That means we have combusted aliquots of the plant material and could quantify the radioactive residues in all. So that means everything which derived from the radio-labeled compound is now quantified. So that means not only the parent compound, not only carbamazepine or only lamotrigine is followed up, but also metabolites, but also, for example, fractions of cell walls of plant material, which is small enough to be extracted. And in the third step, we, if the radioactivity in the plant sample was high enough, we have also done extraction and a specific analysis of these extracts. To just have a look what kind of molecule is it, what the radioactive residue, is it still parent compound, is it metabolite, and so on. And if possible, we have also tried to investigate the soil. but this was also difficult, but I'm coming to this in the end. So just for the experimental timeline of the carbamazepine test set. So we have used carbamazepine in a concentration of 800 nanogram per liter in the artificial wastewater. And we have irrigated with this wastewater 3 liters per day and container. So we sowed the plants, and then they were irrigated firstly with fresh water to get healthy plants, and then we started with a spiked wastewater irrigation. And unfortunately, we have not so much radio label of carbamazepine available, since we have to had it repurified. So the amount was not so high anymore after repurification, but it was enough to irrigate it for 100 days approximately. So we in this 100 days, the concentration of carbamazepine, or in total of the radioactivity, increased continuously. And afterwards, we decided to cultivate the plants further on without any further addition of carbamazepine. So it was irrigated with fresh water. And in this phase, the carbamazepine amount, or the radioactivity amount in the soil, remained constant. So these are the two phases of the test. And in total, we have cultivated the plants over 350 days approximately. So the results of the total radioactive residues, you see here the total radioactive residues expressed as nanogram carbamazepine equivalents per gram. This is important because we don't know if it is carbamazepine. It's all the radioactivity coming from carbamazepine, and it is in the range of 4.2 nanogram per gram up to 17.5 nanogram per gram. It's difficult to see a trend here, so I have converted it into a graph, and here you can see the concentration in plants, again in nanogram per gram. So it's the same values as before, only as a graph. And the blue line is the amendment with the compost only, and the yellowish, orange, reddish lines are the amendments with the biochar compost mixture. And the darker the color, the more biochar is in. So the red one is this one with a 30% biochar. And here in the period where the carbamazepine concentration in the soil is increasing, we see also an increasing concentration of carbamazepine in all fractions except for this red line. It's a bit strange, but okay. And then it remained relatively stable, I would say, over the time, where only fresh water is irrigated. So it seems to reflect the conditions in the soil. The treatment, the amendments with biochar seems to be very similar. So you can't see so much different with the biochar amendments. But we can see that in the compost only, we have slightly higher values throughout the experimental duration. And when we have expressed the the concentration as percentage of applied radioactivity, in this case, we see that only up to 3% of the applied radioactivity was found in the plants. So we have also analyzed plant extract in case the radioactivity was high enough in the plant. And so these are now preliminary results, since we are still working on this last step. So we have found a carbamazepine still in the plant material. The percentage is lower in nanogram per gram, because we also found epoxycarbamazepine, we found hydroxycarbamazepine, and also further fractions or peaks, in this case, radioactive peaks. But this is still ongoing. Yes, and so now we are coming to the lamotrigine results. And lamotrigine was available in higher amounts, so we can irrigate a longer time with lamotrigine. So in this phase, again, the concentration is continuously increasing in the soil. And then we have one sampling where we irrigated with fresh water afterwards. We have applied 650 nanogram per liter artificial wastewater, and again 3 liters per day and container, over a time of about 360 days. So the radioactive residues, it's interesting, seem to be in a comparable range of concentration, from 3.3 to 17 again. So it seemed at first at a bit lower level, but then it increased. I show you again this concentrations of lamotrigine in the plant material as a graph. And as you can see here, again, the line representing the soil with compost only showed slightly higher concentration of lamotrigine. At first, in the first harvests, the concentration in all treatments or in all containers remained relatively stable. But then when we don't irrigate with lamotrigine amended or spiked wastewater anymore, we found the highest levels, which was very surprising for us. We didn't expect this, but okay, this is science. And again, the concentration expressed as percentage applied radioactivity is also on a very low level. It's only 2% in all soil treatments. With lamotrigine, it was really difficult to analyze extract because the concentration level was so low. So we started with the last sampling, and the results until now show that there might be still lamotrigine in the plants, but we would like to confirm these findings once more. So as a last step, we would also like to look at the soil. We have done soil sampling in the end, and here you see such a soil sample. We have sampled the upper layer of 10 centimeters, and you see here also the near our soil in the lower layers. but in the upper layer we found these dark compost biochar mixture, and I think this is a biochar compost mixture with a 30% biochar. When we have done the method development, we could extract lamotrigine and carbamazepine very easily out of the near ore soil only. So it was efficiency over 90% of the radio-labeled. But when we now add our amendments, so the compost and the biochar, and sample the soil in the end, so after aging or cultivation of the plants for 380 days, we can only extract about 30 to 40% of the radio-labeled carbamazepine or 20% of the lamotrigine of the total radioactivity recovered. That means that we have still found radioactivity in the soil after extraction. We can determine this by combustion of the soil, so we can quantify this. And we see that about 60 to 80% of the radioactivity is still absorbed so strong in the soil that we cannot extract it anymore. So there is still residue there. But interestingly, we see that with the biochar, we can extract more radioactivity out of the soil samples that indicate that biochar possibly do not absorb it so strongly as compost. This is a bit surprising for me because I thought that biochar is a very strong absorber of any organic components, but it seems that also compost is absorbing the organic contaminants, and in this case it's radio labeled. So as a summary, we have found total radioactive residue used in plant material irrigated with wastewater, including carbamazepine and lamotrigine, always in the range of 3.3 nanogram per gram to 17.5 nanogram per gram, both compounds. So it's in the same range, and the timely development is difficult to say a trend. So it seems to be relatively stable in the soil when carbamazepine and lamotrigine exist in the soil. The soil amended with the compost only showed slightly higher concentration of the radioactive residues in the plant material compared to the soil amendment with the compost biochar mixtures. Between the biochar compost mixtures, there's not so much difference. And with the soil, we can only extract 30 to 40% of carbamazepine or 20% of lamotrigine out of the soil at the end of the experiments after 380 days. So that means that still a high amount of radioactivity is still in the soil as non-extractable residues. And thank you very much for your attention.
Thank you, Kerstin.
So I'm struggling here with my here.
Okay, so we move to the next presentation. given by José Julio Ortega Calvo from the Spanish National Research Council. And I give you the floor, José Julio.
Yes, thank you, Melissa. Can you see my screen?
Yes, not in the presentation mode. Okay,
now
yes.
Yes,
yeah.
Okay, good morning, everyone. It's a pleasure for me to share our results we have obtained in my group in Seville, in the National Research Council. I will divide my presentation in two parts. The first one, mainly for the external participants, explaining a bit why we have done our experimentation and our contribution to residue, and then a second part more specific on the residue results. Can you see my second slide? Yes, okay, so just as a first introduction, just to say that our regulators, our governors have realized that not only water is an important strategic resource, but also soil. So you can see recent assessment of soil pollution, for example, this one, Food Agriculture Organization, where they have analyzed the main sources of pollution globally or also regionally, and they clearly perceive, like the scientific community, that total concentration of the pollutants in soil is not giving you the right impression of risk assessment, but which are the bioavailable concentration, which are the most accurate for providing you an idea of risk. So, and if you look at, for example, the glossary of this report on global assessment, they give this importance to bioavailability. They explain the different definitions, how to approach that, but basically they don't explain how to use it. To use it, we really need methods to measure bioavailability. And we were lucky that at the start of the residue project, within the framework of retrospective risk assessment of pollution, the ISO method for measuring bioavailability was published 2020. So we have a methodology here ready to use and to apply for the soil, mainly in the retrospective to legacy pollutants that are in industrial sites. And basically the approach is that we were discussing a few years ago that you could really make a line of bioavailable concentration after the fast absorption of the pollutant from the soil. The ISO method proposed 20 hours for desorption in the presence of a strong absorbent or complexing agent like Tinax and cyclodextrin. Then you have the measurement for an estimate for the bioavailable fraction of these non-polar organic compounds. You can also measure bioavailability by passive sampling using equilibrium concentrations. Also as a complementarity with bioassay method that are also part of this international standard. We also propose that this type of methodologies can be applied to prospective risk assessment, to new chemicals, new management practice like the one we are using here in residue with the soil amendments. So the proposal was really try to figure out how to develop fast methodologies and standardized methodologies for measuring bioavailability through physicochemical methods. Later on, connected to persistence of chemicals, but our idea was to apply this methodology in the prospective risk assessment of the application of soil amendments to reduce risk. So basically, the two schools for measuring bioavailability are based on the measurement of the freely dissolved concentration or the fast dissolving concentration. Each of the two methodologies of the two worlds have disadvantages and advantages. If you go for equilibrium sampling, you can have a very accurate measurement of the freely dissolved concentration, which is a minor fraction, minor pollutant mass fraction of the total pollutant, here exemplified as iceberg. Most of the pollutant are present in the sorbent amount, but you can also measure as the fast dissolving fraction in situation of lack of equilibrium that not always occur, especially in soil, where even in the presence of biodegradation, you can have this situation of continuous consumption of the chemical, of release of the chemical. And therefore, you can measure risk through these bioavailability methodologies. So passive sampling are really accurate methods. We have not used them, but I wanted to show them today that they are quite sound methodologies for measuring bioavailability. They are based in a variety of polymers that gives you a good measurement of the freely dissolved concentration in equilibrium with the solid phase. Okay, so these are very sound measurements and can be used for equilibrium partitioning, and also can be used in the estimation of the sediment soil remediation, sediment soil concentration based on the organic carbon content. Unfortunately, there is not standard like the ISO method that I have shown you, but there are some very good studies like this one published in Nature Protocols of ring test, where really good scientists have verified this type of methodology. The second school is the one we have used, and it's based on this ISO methodology to measure bioavailable fraction as the fast dissolving fraction. You can determine the pollutant mass in the soil present as a bioavailable fraction, has a applicability domain, which is with non-ionic chemicals, with the ethanol water partitioning higher than 3, although we have extended this in our project, and therefore you have this methodology. The comparison between the two methodologies, I mean, you can see that maybe the disadvantage for equilibrium sampling is that the long time you need for equilibration, where really many things can happen in the test. No, the advantage is that the desorption methodology is relatively fast, and you can also apply with soils. These are two complementary. We have gone to desorption extraction because it's a very good methodology in terms of connecting with persistence and biodegradation processes. So, for example, in our lab, we have developed this methodology applied to a certified reference soil, measuring the total and bioavailable concentration of an industrial soil, for example, here with benzoyl and comparing with a whole range of tests using 10x extraction. So it's really a good methodology to apply in this project. Basically, the method is based on the biphasic desorption pattern of many chemicals in soil, where you can have a very fast desorption fraction during the first hour, after followed by a slowly dissolving fraction. The method basically characterizes what is already dissolved after 20 hours, which is giving you a good trap for the fast dissolving fraction, which is the most risky and the most bioavailable. So finally, the idea was to apply these methodologies with the residue approaches. For example, here you can see, therefore, in our experiment with pyrene, C14 labeled pyrene, then the presence of biochar layer at the bottom of planted pots with sunflower reduce the leaching of C14 labeled chemicals that are produced due to metabolization. Therefore, the idea is of using biochar or some bioamendments to reduce risk. You can see here this one. So in residue, we have applied this methodology to test the different residual agricultural soils in our institute, and also those soils that you have seen in previous presentation from Israel, and testing the two different chemicals, C14 pyrene, C14 carbamazepine, basically because they are suitable for this type of methodology. They are in the applicability domain of these bioavailability measurements. And the idea was try to combine this persistence testing with bioavailability estimations, including in the research what is happening with if we have partial biodegradation, no mineralization. It means the following the parent and the metabolites produced by C14, and what is happening with these methods if you incorporate the concept of aging in the desorption kinetics. These are the results that you can see with C14 before the test, the persistent test. You can see that in terms of C14 binding, you have a relatively high bioavailability, which is reduced by the addition of a local compost. This was in our agricultural station soil before we received the soils from the residue project. We were waiting for that and developing our methods. You can see, therefore, that Tinax extraction can give you very good measurement of these differences in bioavailability. When after this period of persistent test, you can see that biodegradation leads to the formation of metabolites that are given by these light green and brown boxes as compared to the parent chemical. We got a recovery of 100% of the total C14. Therefore, you can see that after the persistent test, we see a shift in bioavailability. The biodegradation of pyrene is occurring up to 40%, but the metabolites in the presence of this compost amendment changed from being bioavailable to being really part of the non-dissolvable part. So this means that biodegradation of this chemical changed the risk in terms of the presence of these metabolites are part of the non-bioavailable fraction. So in this case, incomplete metabolization of the chemical leads to a reduction in the risk of the chemicals. What happened with carbamazepine? Carbamazepine has a log KOW of 2.7, which is a bit at the limit of applicability of the ISO method, which is around 3. So the idea was try to extend this applicability domain to carbamazepine. And you can see here that before and after the incubation, the kinetics of the absorption of the chemical change very clearly. Before and after aging, you can see that the fraction of the fast dissolving chemical is decreasing, and the rate constant of the desorption is also decreasing. So this means that the parent chemical before and after incubation dissolve more slowly. So this is therefore a decrease in bioavailability. So we applied this methodology to this chemical. You can see here that if you look at the compound in the aqueous phase during this Tinax extraction, you can see also that before and after the incubation, the aqueous concentration in the Tinax extraction is going down nearly to 0, therefore allowing this Tinax to act as an infinite sink. So if you apply this methodology to this soil and also to look at the carbamazepine bioavailability, you can see that for sure you have to take into account not only what is going into the Tinax, but also what is going into the water phase. So, but still in this case with carbamazepine, the amendment had not a big impact on bioavailability before incubation, but after incubation we get some surprises, as you can see here, and especially in the amended soil. You can see that the bioavailability is mainly due to the presence of the metabolites that go to the Tinax and to the water phase, while the parent chemical really goes to only the Tinax, or the Tinax peak, which is represented by these darker boxes. The light boxes are the metabolites. So the big difference here is that although the transformation of carbamazepine after 60 days goes to make that the parent chemical dissolve more slowly, the formation of the metabolites contribute to risk due to the presence of this tendency of these metabolites to be in the aqueous phase. Okay, so this was the situation with this soil from the institute, from agricultural soil with low organic matter. And then what happens with the residual soils that receive from Israel? We applied this methodology, and you can see here that the different compost that contain different fraction of biochar, the other groups have explained quite well the origin of this compost containing highly condensed biochar carbon produced by phyto. You can see here that the bioavailable fraction determined by this 10x extraction is going down as long as the biochar content increases. After this persistent test, you can see that that very clearly the bioavailable fraction decreased enormously, and especially this is very striking in the compost number 4 with 30% of biochar in this composition. Therefore, showing that these methods can be really applied for quickly assess this type of amendments that is designed to reduce risk due to this sorption capacity. We wanted to look at what was happening with the desorption kinetics, and with this this soil amended with this 30% biochar containing compost before and after incubation, you can see very clearly that the kinetics of desorption of the parent chemical changed enormously. So the fraction of fast desorption decreased, and also the rate constant of the fast desorption and slow desorption. So we applied the same methodology to the distribution of the carbamazepine in different phases of the TINAX extraction. We could verify very similar results to other groups. So with the soil only, we could see that 100% of the chemical was bioavailable, which is really very, very interesting. This could change slightly by before incubation with the amendment of the compost containing biochar, but after incubation, you can see therefore that the transformation of the chemical in the soil, especially in the amended soil with biochar, led to a very strong decrease in bioavailability, and also affecting the metabolites that were in the aqueous phase. In this case, we can verify, therefore, that the use of this amendment is a success in reducing the risk coming from this chemical and the subsequent transformation in soil. So as a conclusions, we can say that message that total concentrations are giving you enough overestimation of risk, but you can get more realistic assessment with bioavailability that can be measured by free or fast dissolving fraction. We propose this type of methodology integrating with other persistent methodologies and also prospective scenarios like the design of soil amendments. And with pyrene and carbamazepine, we saw two different things. With pyrene, we can see that transformation is going to reduce the risk to these non-desorbable metabolites, and with carbamazepine, you can see that the metabolites can be released into the aqueous phase and then having contributing to risk. So thank you very much for your attention, and to the PRIMA and the Spanish Ministry of Science and Innovation. Thank you very much.
Thank you very much, José Julio. I don't know if there are some questions. No. Okay, so the next is is me. So I just give a very brief synthesis of what dissemination and communication activities that have been done during these years. So just 1 second. Okay, now you can see my screen. Okay. So from our side, just a very brief introduction about who we are. So Consorzio Italbiotec is the first Italian non-profit organization in the biotechnology sector. It was born in 1998 and it has grown a lot over these years. And coming up to now, where we account for more than 160 shareholders among Italian universities and research institutions, and more than 120 private companies and startups that works mainly in the 3 areas of biotechnology, so on the agri-food, life science, and bioeconomy, circular economy. What we do, we are specialized in 3 main areas: the areas of strategic grant consulting, so on all the area of European funding programs consulting. The second area is more technical and is more related to the innovation management. So we perform different types of activities related to business plan development, market analysis, but also impact analysis such as LCA, social LCA, and so on. The third area is instead related to the communication and dissemination activities. In fact, in the RESIDUE project, Consorzio Italbiotec was the responsible of the communication and dissemination activities related to Work Package 7. This is just an overview of all the tasks we performed in these years of the project. So starting from the setting up of all the communication and dissemination strategy with a plan, the communication toolkit with the logo, the elaboration of the roll-up, and the leaflet to share all the residue-related topics and the benefits from the residue project. The digital activities, which comprise the elaboration of the project website, the Twitter account, and the participation to congresses such as the CETA, which is the worldwide professional organization dedicated to the environmental science and environmental management. So different residue partners participated during these years by presenting posters about residue topics. Also this year in Segui. And then we made our first workshop, an online workshop, on April 2022 about residue themes. So the advancement of the technological aspects of risk reduction strategies related to the irrigation with wastewater and the fertilization with sewage sludge. And we had almost 50 participants. And last year, instead, we organized a summer school for students and PhD in Milan. So it was the first time that we see each other in person. And it was a 2-day school regarding in which project partners gave their lessons about innovative agronomic practices for healthy soils and sustainable farming systems, We had almost 15 participants, and it lasts 2 days. The first day was more dedicated to lessons, and the second day, instead, we had a field trip in a company which produces biochar in the area of Milan. So there are some photos of the event. And we published an article for a divulgative magazine regarding new techniques for sustainable agriculture. If you want, then we can, after the event, we can share the slides on the website, and you can just click on the link. Sorry. And as final, we dedicated during the last year in the elaboration of 2 documents. One is more related to the legislative context, and it is a position paper. It is essentially a literature review in which we collect information about the main policies and practices linked to the use of wastewater and sewage sludge in the countries involved in the residue project, so in Italy, Spain, Germany, and Israel. The document is made up of 8 chapters, starting from the context, so the water consumption, the European directives on clean and safe water, the state of irrigation, of the water consumption for irrigation in the 4 countries, other policies and European directives regarding the use of wastewater and sludge, but also directives regarding the application of circular economic practices for the sludge recovery, and a more detailed a section on the wastewater and sludge policy in the specific countries involved in the project. And then a last part of recommendation that I have essentially synthesized here. So the harmonization of policies seems to be crucial for promoting the adoption of practices such as the one from the residue project, and also to ensure the safety of the agricultural products. So this paper would like to recommend the harmonization of policies and practices in order to create a regulatory framework consistent and that support these practices. And this includes the establishment of clear standards for water quality, the improvement of monitoring systems, and also the promotion of the use of treated wastewater and sludge in agriculture. So this is the document. It is a deliverable, and will be published on the website. So if you would like to have a look at the document, you will find it on the residue website. And as a second document, this is a manual for the transfer of the project results. It is a guide essentially for farmers. And it is a really practical document in which we give practical advice on the use of biochar as a soil amendment. And these are the main key points of the document. So starting from the use of biochar, its production methods, the properties and its applications, but also the impacts at environmental and socioeconomic level. There is a part on practical guidelines and also market prospects. And this includes also the further integration of biochar with wastewater and sewage sludge treatments in order to promote circular economy in the agricultural sector. This is just a preview, and also this will be published, so you can go and read it. And this is just all from our side. Okay, so I don't know if there are any questions, or if you would like to enter in contact with us, you can go to the Residue website. We will publish the slides with all the contacts, or also you can write us through Eventbrite, and we will try to direct the communication to the partners. So thank you very much for your participation, and thank you to all the speakers for their very interesting presentation and for the results achieved during these years.
Yeah, thank you very much, Melissa, to you and also to Italbiotec to organize all this meeting. I think it showed again impressively how successful our project was. I mean, now the last task will be, again, important to bring all the results together, to put it in a nice, not in a nice, but in a meaningful project final report. I think there is still a bit work to do, but in the end, to all participants, if you're interested, we will let this webpage a bit open. Also, the final report, as long as we can publish that, as we are allowed to publish it, it will be found, or it can be found later here when it's done and approved by PRIMA. So, as I said, we were successful in a very difficult environment, and I hope for upcoming projects in this, just to follow up that.
Thank you. Thank you very much. So we can finish the meeting. There are no questions.
Yeah, if there are no more questions, yes.
Yeah. Okay. Thank you very much to all.
Yeah.
Thank you, everyone.
Goodbye.
Okay.
Goodbye,
Thank
everyone.
you. Goodbye.
Goodbye.
Thank you.
Bye.